today's course, my plan is, I think, just to finish off this remainder estimate, and then maybe one section in the chapter. So this is, I think, a general estimation for using the remainder. So we can think the R for the remainder is like an error, like an error. So we can think like if we take the this underestimate or overestimate. So we have some area that is not the real area. Right? So if we look on the left, for example, we see that there are area that is missing, which means the curve, the area is larger, right? And we have the other possibility is we have the overestimate area, which means the curve is below, right? Below the area, the under the curve, right? So we can simply write that based on the integrations. So from the n plus 1 to the infinity, we have the improper integral with the function of x, and then it less equal with our error, and then our error also less than the improper integral from n to infinity. I think we can also I think let me give you an example how to use this conclusions. So let me give you some example here. So approximate sum of the series by using sum of the first 10 terms, and then our goal is to estimate the error. Okay. So let's say we have our functions is 1 over n cubed, but let me write as a function of x. So let function of x equal 1 over x cubed, like that. So probably we could take the improper integral. So take from n to infinity, okay, and then take the limit fx dx, and then take the limit. Let's use t. Okay, usually in calculus improper integral, we usually define a new variable that's going to be approaching infinity with t. Okay. So this will be n t 1 over x cubed dx, and then limit st getting infinity, and then we are going to take this integration. So we have 1 over 2x squared, right? And this is n, this is t. So we get that limit. Still we have the limit, and we have negative 1 over 2t squared, and then minus minus plus, right, 2n squared, and this is going to be 0. So we have our improper integral solutions is 1 over 2n squared. So this is the 1 over x cubed dx, okay, is equal to 1 over 2n squared. So we have the integration part, and then the questions also mentioned that we need to use the 10 terms, okay, the first 10 terms. So we don't have any other choices, so that we need to compute one by one. Okay, so 1 plus 1 over 2 cubes, and then plus plus plus. Okay, so we got to
get some information. So why we need to do this? Because this is actually the real calculations, right? And then we are going to take these calculations and compare with the integrations, okay? Like how much the difference, and that will be the error, okay? So let's take the sum of this. And then we could just take that as approximation because we are being told that using 10 terms, so S10, so our partial sum with n equal 10. So this will be 1 over 1 cube plus 1 over 2 cube plus 1 over 3 cube and plus until 10. And I think you can just use your calculator. Okay? And it's approximately 1.197. Right? And then, based on what we have in the in our integrations, remember that the remainder is in between, right? Or if we take these integrations, then the remainder need to be okay. And then the n is 10, okay? The n is 10, so R10 should be less equal. This is from 10, 1x cubed dx. So we are going to use this 1 over 2n squared and then take the n equal 10. Okay. So 1 over 2 and then 10 squared, or 1 over 200. So size of the error is 0.005. Okay, so this is, so 1.197 is approximating with n equal 10. And then this one here, the remainder, is the error. Okay? The error that we have when we have n equal 10. So this is answering the approximations. So this will be answering approximate with n equal 10. And this is the size of error, or error estimation. Okay. And basically what you need is to compute, okay? To compute using some partial sums. But sometimes the questions can be varied. Like for example, you already have the numbers, but you need to know what n. So you could a little bit reverse this. Questions. Like for example, we can have a follow-up questions like, we have error 0.005. What if we want to make the error maybe smaller? Okay, so suppose that how many terms, maybe that will be how many terms required to make the sum, accurate within 0.0005. So this is asking, so if you, sometimes the question maybe they write error or maybe accuracy or accurate, but they are the same thing. So we need to make sure it's accurate with the range of 0.005. It means that this 0.0005 is the size of the error. Okay. So we are going to start from here, and we are going to check, and then what will be the best n that is going to be approaching this error. Okay. So we could start, because we already found our integration, so we could start with, I think let me make smaller this part here. I think too much here. Let me resize this for a while, and then we can have. So the size of the error, we know that the size of the error, or R, should be this, right? At most is this one is the maximum error that we can have, and then we have the error should be less equal with this integrations, right? Which we already calculate, and this is 1/2n squared. Okay. So what we did is we are going to take the comparison between these two. So 1/2n squared. Let's say we need to make it less than 0.005. And from this expression, we could have solutions for n, like the n squared, at least need to be greater than 1/0.001. So we just multiply 2 with 0.005. Or we could have a 1,000. So squaring the 1,000, so n should be greater than this. Or take your calculators, and then we can compute this maybe around 31.6. And since it's not a whole numbers, right? Not an integer, so we need to complete the numbers, and maybe we could say, so at least we need 32 terms to confirm error is 0.0005. Okay. So actually it's pretty logical. So you just need to keep in mind this relation. The error is always less equal with the improper integral. Okay. So this is the estimations. So still in the estimations, we could also try to change a little bit the formula, but actually this is still the same. So let me go to here. So let me write first. Okay, I think at the yesterday class I mentioned that the R is S R plus and yeah, S minus Sn, right? So this is the real value, and then the Sn is our approximation. So the Rn is the difference between that. So let me write again the formulation. So if we add plus Sn, so if we add to the whole equations, so if we add plus Sn, which means we are going to have Rn plus Sn, which is equal to S. So we are getting this another equation that can be used. So we are going to express this inequality with S and also Sn. So for example, the n that we did before, the previous question. So suppose n is equal 10, and then we are going to evaluate this series, the same function, so 1 over n cubed. Then we can also using this formula to express our solution. So for example, this become s10 plus, this is n plus 1, so it's become 11 to infinity. And this become s10 plus, this is 10 infinity fx dx. And we already compute the integrations, right? We already compute that the n, this is equal to 1 over 2n squared, right? So we could just exchange with 1 over 2n squared. And then we also, I think we also have compute the s10, right? From the previous calculation, which is 1.197 something, right? So we can take all these numbers and equations inside the inequality. So we could get more, I think, a good visualization for the range of the error. So we could get directly, for example, we try to write this 1 over 2n squared, but we are using 11, so 11 squared, and it's less equal s, and then less equal 1.197, and then plus 1 over 2 10 squared. And then we can compute this, and somehow we get that this is going to be okay. And I think one way to get what will be the error is we can try the midpoint. Okay, we have the least minimum, right, and then the maximum one, right? So maybe we could take the endpoint, what will be in the middle. Okay? So we could, and this is just approximation. So approximate the s by midpoint. So we are going to check the center, okay, of this number, and then we get that it's around 1.2021 something, and we get the error, the maximum error is 0.0005. This is you get from your calculators. Okay, you can check like what will be the possible error. And I think if we compare this to the previous one, I think there will be a little bit difference in error. Okay. We need to use only 10 terms to make this error. Okay. So to make this error within this, we can use n equal 10. But in the previous one, we need to get 32. So it depends on how we need to look at the visualization. If we need to make it clear in terms of s, I think we can just directly go here. But if you need to make sure that you want to go through the error itself, I think you can use the previous one. Okay. Both of them, they are actually the same, but maybe the result will be a little bit slight difference. Right? Both have some different results. Okay. Okay, and that's it, the estimation of the sum. Okay. And sometimes understanding the error also can be helpful for, I believe, if you need, or if you work with a lot of data, statistics, you need to understand the error. Okay. Like usually every data that has been analyzed, they will have like standard error or standard deviation. Right? And I think no matter where you work, like you work in the industry or maybe related to finance or maybe related to retail company, all companies will have like a database and you need to work with error. Okay? So sometimes understanding what error means is, I believe, is important. And especially if you want to be like data scientist or data analyst, you need to understand a little bit statistics. Okay. So calculus is actually like it's like a rough work of the statistics, the fundamental part. Okay, we go to the next one, which we have the comparison test. Okay, so before I give you the definition for the comparison test, so let's consider the series. Okay, let's consider this. So we know that if we take this into like take the few terms. Okay, so n equal 1 is 1 over 2, and then 1 over 4, and then 1 over 8, 1 over 16, right? We can also getting this as a, so we can see that this is multiplied by half, right? Half, right? So we could say that r is half, and we could write this formulations in geometric, right? With this 1 over 2 is the first terms, a. So we know that this is geometric. Okay, we can see that this is geometric. And then the r is less than 1, it's half. So we know also that we could have this sum. We could take this into our formulation of the geometric a over 1 minus r, which we can compute, and we know that this is, it should be convergent, right? So it should be convergent for sure, right? But then if we had another series that it looks like similar, but there will be some differences, okay, like that. So we add plus 1 in the bottom equation. So we know this convergent. And then how about this series? Okay, so if we compare this one, okay, if we compare, of course, if you add plus something on the bottom side, it will give you smaller, right? Getting smaller value than this one, right? So you could say that the left is less than the right. Okay. So if we take the sum of the series, if this is convergent, this must be convergent, right? Okay. So if we know that this is less, and this is convergent, series is convergent. And then this also has a smaller value. So this series also convergent. So we have this definition now. So suppose that the series AN and BN, they are series with positive terms. If the series of Bn is convergent, and the An is less equal to Bn. That's similar to what we have in the example. And An also convergent. The second one, you need to see clearly what does it say. If the series of B diverge, and A is greater than B, now A must be divergent. Okay. But you must be careful. Okay? So if we, for example, we know that B is convergent, but we see that B is maybe less than A, and we are not sure A is divergent or convergent. So we need to make sure which one is the larger one, and then when we find one of them converge or diverge, we need to make some conclusion. Sometimes the conclusion may be a little bit different. Like, for example, if B and converge, and then B, for example, if B is smaller than A, then we cannot conclude. Okay, we cannot conclude. So we need to make sure this is happening. Okay. This is what we call the direct comparison test. So we directly test the series and compare with another series. Okay. So for example, if we sometimes the question is like this, okay? I will give you a hint and clue when we are going to use this series. For example, determine the series converge or diverge. So mostly chapter 11, the question will be asking converge, diverge, and then converge sometimes you need to compute how much the value, but sometimes it's just asking converge or diverge. Like the comparison test, we don't need to know how much does it converge. We just say, okay, it's converge, it's diverge. Okay. So for example, question like this. So you see some numbers constant, and you see it's a little bit having a polynomial degree at the bottom, 2n squared plus 4n plus 3. Immediately, what you can think is, you can compare this to just 1 over n squared, or 1 over 2n squared, right? And then, or maybe 5 over 2n squared, and we can see that directly, oh, we can compare this. If we are trying to work out this, maybe divergence test, take the limit, and of course limit, it doesn't give you anything. It's equal to 0. Remember, if we take the limit and if it's equal to 0, then we don't have any conclusions. But if this limit has a value or it doesn't exist, it means we can just say, okay, it's divergent. So the very first, test the divergence. And the second, if you see this, you take the limit and it's equal to 0. Another test that I think easy to come is the comparison test. Can you find any function or any formulation, any expression that can be compared with this easily? Like I said before, we can easily compare this to, so suppose observing the series 5 over 2n squared. Okay. And because for sure that because of this plus 4n and plus 3, if we compare this to this will be much more smaller. And we know this is converged. Okay? How do we know this converged? Every time we have 1 over n with power of p, like this, we can take the p series. Okay, so whenever we have this, so whenever we have this, if p is greater 1, it will be converged. Okay? Sometimes we're using p or r, the same. So p greater 1 is converged. p less equal 1 is divergent.
So we see this 1 over n squared, it must be converged. Okay.
So we say that this is converged. And then observe that 5 2n squared plus 4n plus 3 is less than 5 over 2n squared. Then the series is convergent by direct comparison test, or you can just write comparison test is okay.
The idea to use this method is to think is any other function or series that can be compared with, and you need to make sure that this is happening. Sometimes if it doesn't make sense, for example, you find the other series convert but it is maybe greater, then you need to think with another method. For some series this is, I think, quite helpful, but most of the time maybe there's another method that better than this comparison. We call that method the limit comparison. Okay, I think that will be the last point for our course. Okay, the limit comparison. Okay, okay, I think we can take this. Okay, so limit comparison, okay, before we define what is that. So let's say we are taking the similar series, but now it's not plus 1, but it's going to be negative 1 like that. So we are comparing with this. So we see that this inequality, it will be useless, right? So what do we do, right? Now, in such case like this, we can use what we call the limit comparison test. So let me write here. So we can use direct comparison test. Okay. So the idea is, suppose that the A and B and they are series with positive terms, and if we take the limit as n approaching infinity, and take the ratio between these two series, A and B in our sequence, should be equal to constant using the limit. So C should be a finite number and it should be positive. It should be positive. So if this happens, then either the A and B, they are converged,
or they both diverge. Okay. So we need to know, for example, we are going to compute A, and we know that B is converged. And then it has to see when we try to take the limit between these two ratios. If the B converge, then A also converge. And we can also make it, if B diverge, then A also diverge. So let me give you an example how to use this. Okay, just a quick example. For example, we want to take the 1 over 2 with power of n minus 1. Okay, let's say we are going to test this convergence or divergence. Okay, so converge or diverge. So suppose that we take the A. Maybe A is the question, and then B is our known series, which is the we know that this will be converged, right? The geometric one. And then we take the limit, and then don't worry about A and B. You can switch A, B as long as you want, okay? Because that's only ratio, and it doesn't bother the definition. So let's say we take this limit, okay? Take the limit. So this will be 1 over 2n, 2 power of n minus 1, and this is 1 over 2 power of n. Okay, I think we can take the limit, and this will be 2 power of n, and 2 power of n minus 1, right? And directly you can see that we can divide by the highest power, which is the 2 power of n, it's the exponent, and we can define 1 with 2 power of n, which if we take the limit is 0, right? So directly we can write that this in turns become 1, 1, and we could see that this is equal 1. So we see that this is greater than 0, right? So because the result is positive, then because the series 1 over 2 power of n converge, then the series also converge. The problem within this limit, or within this limit comparison, is if you get the result 0, then you cannot make conclusions. That's the only problem. As long as you get positive, I think you can solve the problem. Okay, you can solve it. There is also estimating sum, but I think I will skip for the comparison. Skip this this time. Okay. Okay, so maybe we got a little introduction for the alternating series, and I will review again next week. On Wednesday, also Thursday, we are going to focus on alternating and maybe the other part as well. So let me go through the definition first. Let me write here. Let me write using this one, alternating. So alternating can be, for example, let's say start from 1 half and we say that this is 1 over n like that. Or maybe another example. This is two different series. So either you can have the -1 n minus 1 or -1 with power of n. Okay, both terms will make the series alternated. Okay. So in general, you can have an equal -1 n minus 1 bn, or an is -1 with power of n and then bn, which means that you could ignore -1 and you see another sequences or another series that is defined by this b, and the whole thing we call the alternating series. Okay, this we can make it as -1 with power of n minus 1 or -1 with power of n. Both will be alternating, but maybe the first one start from positive, the second one start from negative. Okay, and this is usually the default terms. You could think like maybe you can use also n plus 1 and it would be the same result, but by default usually we write only this or this. Okay. Okay, maybe before giving you the proof, let me just write the definition that if we have, let's say this equal to b1 minus b2 plus b3 minus b4 plus b5 minus b6 plus ... And we know that the bn is positive, okay, and it satisfies 1, okay, that the bn plus 1 is less equal bn for all n. So we know that it will be decreasing. So let me write here, decrease. So it's similar to the integral test. The requirement is to need to be decreased. And the second, the limit is equal 0. If this satisfies, then series is convergent. So actually it's pretty easy to see. So as long as you can see not the value, see only the b. Okay. So maybe this is 1, this is half, 1 over 3, 1 over 4. You see that by the numbers it's decreasing. So first, okay, we get that, okay, the numbers decrease. So ignore the positive negative. So ignore it for a while. And then we take the limit of only this b. For example, b is 1 over n. N is equal to 0. Remember, yesterday we set a statement that 1 over n is a harmonic series which is diverged, right? But if we take it in alternative sequence like this, alternating sequence, it will be converged. You could imagine, like 1 and then half and then 1 over 3. If we plus, it will be divergent. But if we have 1 minus half plus 1 over 3, you can see that it's going up and then going down, but it's a little bit and then going up a little bit and then eventually it reaches 0. Okay, can you imagine that? So you can imagine, like let's say we have the -1, like for example this. Okay. So we start from 1, so we have 1 and -1 here, and then it's going up. Maybe this is 1 also, it's maybe here, the second one, and then the third one is going to be here, maybe a little bit going here, and maybe the 1/4 is going to be here, and it's going to be here, and you will see that it's going to be reach 0, right? So we take all things like that. Okay, so 1/n limit 0, and then we know that every value is getting less and less, decreasing. Okay, I will give you more about this next week.